one of the properties of a solid is melting point. And so again, melting point primarily going to be affected, just like boiling point, primarily going to be affected by how strong the intermolecular attractions are. Right? So when I have these three, the water, the ammonia, and the HF, they are all capable of hydrogen bonding. So when they freeze, they line up and make these strong hydrogen bonds. If I want to melt that solid where all the particles are organized, maximizing the hydrogen bonds, and allow them to flow past one another, in order to melt that solid, I've got to break some of the hydrogen bonds between this molecule and its neighbors to allow them to flow past one another. That takes more energy, it takes a higher temperature. So when I don't have the ability to make hydrogen bonds, it doesn't take as much energy to cause the molecules to break their weaker dipole-dipole attraction. So then why does after that point, why does the melting point keep going up? Or why is the melting point of HBr higher than HCl? I mean, HBr versus HCl. The Cl is more electronegative than the bromine. This should create larger dipole-dipoles. And this should create a smaller dipole-dipole. So if the HCl has larger quantities of partial charge, shouldn't it attract its neighbors better and require a higher temperature for them to flow around and melt than the HBr? Why would the HBr have a higher melting point? Right, it's the London force. Right, so what we just said was, and this goes for the properties of liquids, their boiling points, and the properties of solids, their melting points. Hydrogen bonding is special. If you have to compare a molecule that can hydrogen bond versus one that can only form dipole-dipole attractions or London forces, the one that can hydrogen bond should probably be experiencing much stronger attractions, and that's going to take a higher temperature to break those attractions and melt it, or break all the attractions and convert it into a gas. But when you're comparing, so if we ignore those three then, and just look at the other ones, when you're comparing particles that can only undergo dipole-dipole or London forces, like HBr and HCl, cannot hydrogen bond, but they can form dipole-dipole. If they're forming the same types of attractions, they're both forming dipole-dipole, then you want to look to the London forces. If they have the same type of attractions, whichever has stronger London forces will probably be the deciding factor. So we can say that here. The bromine is a much larger atom than chlorine. It has a lot more electrons around it. Its electrons are more fluid. So even though, just based on the electronegativity difference, we would predict the HCl should be more polar and form stronger attractions, it's actually the HBr that is really more polar because of the fluid electrons extra shifting, creating extra partial charges. That's going to allow the HBr molecules to attract one another more effectively. With melting point, it's not just about the intermolecular attractions. That is the primary factor. So melting point is affected by really two things. One, the strength of intermolecular attractions. And then two, the next factor has to do with how tightly packed the solid can get with its organization. So this would be having to do with the effectiveness of the packing. The packing effectiveness. So what I mean by that is, are there gaps between the molecules when they pack close together? The sizes of the molecules such that I can't really pack them in an organized, efficient way that minimizes the gaps between the molecules. So if there's more space or gaps, they're probably not going to be able to get as close together and attract, and that would usually only result from a situation where their shapes don't allow them to be packed in an organized way. Okay? So that comes back to the like the butter versus olive oil example. The olive oil molecules have a bent shape, so it's harder to pack them in an organized way. So olive oil has a melting point that is lower, and at room temperature it's already melted. It's already become a liquid. Whereas the butter is a solid at room temperature, barely, but it is, because the molecules can pack closer together. In both olive oil and the water, the molecules have the same types of intermolecular attractions. They're both weak London forces attracting them together. But when the molecules can pack in a way where they can line up nice and form nice intermolecular attractions, then the organization and the packing efficiency allows them to be more solid and require more temperature and a higher melting point to get the particles to flow past one another. And so this table shows a variety of melting points as well. So we can see the type of attraction is really important. Molecules that can undergo hydrogen bonding have a higher melting point. The ones that cannot have, in general, a much lower melting point. Yes? Yeah, so what we said was, excluding these 3 points here, just looking at all the other points, they go up as you go to the right. And that's because as you go to the right here, we're involving atoms that are one more level down on the periodic table and have larger electron clouds with more fluid electrons that can shift around and create more significant partial charge attraction. So this one just points out again, if it only has dispersion forces, it's probably going to have much weaker attraction, and it's not going to take much energy. And even at a very low temperature, it's already melted. It's already become a liquid, or even, depending on the substance, possibly a gas. Now, if I have actual ions, a full charge attraction, then I'm talking about hundreds of degrees Celsius required to break those attractions and get the particles to move around. So it's the type of attractions, the quantity of charge that's the major thing. If I'm looking at two different things that both have dispersion forces, though, if they have the same types of attractions, then I need to look at their electron clouds and see which has a bigger electron cloud that can allow electrons to shift around more. That should be the one that creates stronger attraction. Solids sometimes can also have a vapor pressure. So we talked about vapor pressure for a liquid, but solids can also have a vapor pressure. Usually that is true for solids that are nonpolar. So mothballs are made from naphthalene, and that is a fused system of carbon rings where the carbon atoms have some double bonds here, and each of these carbons here has an extra hydrogen attached. But the symmetry of this molecule, the fact that there are no highly electronegative atoms, means that it's going to be nonpolar. Right? So there are a lot of atoms and a lot of electrons in here. So that means that this molecule has its electrons, and they can shift around pretty easily and create some areas of partial charge so that one molecule can maybe stack on top of another and form some nice London force attraction. Right? But remember, the London force attractions, even though they can be strong if there are a lot of electrons shifting around to create some significant partial charges, they still are only temporary. Because if the molecule is nonpolar, then the electrons shift to one side and create some partial negative on one side. They could then shift back and be evenly distributed for a moment. So in that moment in time, when this naphthalene molecule has its electrons actually evenly distributed instead of shifted around to create partial charges, how much attraction does it have with the neighboring molecule? 0. If it happens to be that moment in time where its electrons are not shifted to one side or the other, creating these temporary charges, and the electrons are evenly distributed and there are no temporary charges, it doesn't have any attractions with its neighbors. So what is it going to do? It will just evaporate right off the surface. So that is called sublimation. Subliming, or sublimation, is the process where a solid goes directly to a gas. And that's mostly common with nonpolar substances. because these nonpolar substances can form nice London forces, and when they organize in the Rosen columns into a crystalline solid, that maximizes those London force attractions. But the ones on the surface, once in a while, well, their electrons will shift into a way where they don't have any partial charges in that moment. And if they don't have any partial charges and they do still have some motion, right? They're not just sitting there perfectly still, they're still vibrating, something might collide with them, and so they might just leave the surface of the solid as an individual molecule in the gas phase. And that is the sublimation process. So if I take this powder in a container and I seal it with the cap and just let it sit there over time, I will see the solid deposited on the inside surface of the container, because some of these molecules on the surface of the solid sublime, become a gas, and then their electrons might shift back and create polarity again, and then they might start to form a solid and line up again on the inside surface of the container. So I can see that with mothballs, with naphthalene. I can also see it with iodine. If I take solid iodine, which is this purple color, and I just have it sitting there in the bottom of the container, the iodine molecules, which are nonpolar, can shift around and create charges to attract. So that's why it's a solid and not a liquid, because they line up and form these nice London force attractions. But sometimes the molecules have their electrons shift back in an even distribution and they're not charged anymore, and then they don't have the attraction, so they sublime and become a gas temporarily. So there would be an equilibrium created where a few of the molecules at any moment would be in the gas phase, but most of them would be forming those London force attractions and staying in the solid phase.